Something is pulling us, not you personally, not the Earth, not even the solar system alone. The entire Milky Way galaxy, a disk of stars and gas and dark matter 200,000 light years across, containing somewhere between 200 and 400 billion stars, is moving through space at a speed that has nothing to do with its own rotation or its local gravitational environment. It is being pulled, drawn, along with thousands of other galaxies in our cosmic neighborhood, toward a single region of space at a velocity of approximately 600 kilometers per second. 600 kilometers every second. The Earth orbits the Sun at 30 kilometers per second. Our galaxy is moving toward this region at 20 times that speed, and we cannot see what is pulling us. Not because our instruments are inadequate, not because we have not looked, because the thing doing the pulling, the mass concentration responsible for the motion of our galaxy and thousands of its neighbors, sits hidden behind the densest, dustiest, most optically opaque region of our own galaxy. The stars and gas and cosmic dust of the Milky Way's disk block the light from anything behind it in that direction. A vast region of sky, a band running along the plane of our galaxy, where optical telescopes see nothing useful, where the view is obscured by our own home. Astronomers call it the Zone of Avoidance. And behind it, in the direction of the constellation Centaurus, sits something so massive that it has been redirecting the motion of our galaxy for billions of years without our knowledge. They called it the Great Attractor. The name is not poetic license. It is a description. Something great, in the sense of vast and massive beyond easy comprehension, that attracts, that pulls, that draws toward itself everything in a region of space hundreds of millions of light years across, with a gravitational influence so pervasive that nothing in our cosmic neighborhood is moving in a direction entirely its own. To understand how we found it, you have to understand what was expected. In the cosmological model that astronomers work with, the standard model of cosmology, built on general relativity and confirmed by decades of observation, the universe on the largest scales should look roughly the same in every direction. Matter should be distributed approximately uniformly across the cosmos. Galaxies should be moving apart from each other as the universe expands, each one receding from every other at a rate proportional to the distance between them. This is the Hubble flow, the smooth, orderly expansion of space that has been carrying galaxies apart since the Big Bang. In this smooth picture, galaxies have what astronomers call a recession velocity, the speed at which they are moving away from us due to the expansion of the universe. But they also have a peculiar velocity, a velocity over and above the Hubble flow caused by local gravitational influences. The gravitational pull of nearby galaxies, galaxy clusters, and the large-scale structure of the cosmic web all add small deviations to the smooth expansion. Small deviations. In the 1970s and early 1980s, a group of astronomers began measuring the peculiar velocities of galaxies in our cosmic neighborhood with unprecedented precision. They called themselves the Seven Samurai, a group of 7 researchers who spent years painstakingly measuring the distances and velocities of hundreds of elliptical galaxies across a large region of sky. What they found was not small deviations. What they found was that our galaxy, along with the entire local group, along with the Virgo cluster of galaxies, along with an enormous volume of space containing thousands of galaxies spanning hundreds of millions of light years, was all moving in the same direction at the same extraordinary speed, 600 kilometers per second, toward something in the direction of the constellation Centaurus, something that was not in the catalog, something that could not be seen directly, something that was pulling on an almost incomprehensible scale, generating a gravitational influence powerful enough to redirect the motion of our galaxy and thousands of its neighbors, powerful enough to overcome the Hubble expansion across hundreds of millions of light years, powerful enough to have been doing this since long before any human being looked up at the sky and wondered what was out there. The Seven Samurai published their results in 1988. The term Great Attractor was coined by one of their number, Alan Dressler, and it entered the vocabulary of cosmology immediately and permanently. Not because it resolved the mystery, but because it named it. Because it gave astronomers something to point at, a direction, a distance estimate, a gravitational mass calculation, even if what it was pointing at remained hidden behind our own galaxy. The discovery raised an obvious and urgent question. What is it? If this is the kind of content you want more of, subscribing to The Cosmic Depth takes 2 seconds, and we post new documentaries every few days. Because the answer, when it came, and it came slowly piecemeal, through decades of increasingly sophisticated observation using instruments that could see through the zone of avoidance in wavelengths that dust cannot block, turned out to be both more and less than the mystery suggested. More, because what lies in that direction is genuinely enormous, a concentration of mass that dwarfs anything in our immediate cosmic neighborhood. Less, because the Great Attractor itself, the specific overdensity that the Seven Samurai identified, turns out to be only part of the story. Perhaps not even the most important part. And the full story, when you follow it to where the gravity actually leads, takes you somewhere considerably further than the constellation Centaurus. Somewhere that makes the Great Attractor look like a local detail in a structure so vast that the mind genuinely struggles to hold it. The zone of avoidance is one of the most frustrating facts in observational astronomy. Imagine trying to understand the geography of a continent when a thick, impenetrable fog covers exactly the region you most need to see. You can map the coastlines, you can explore the accessible interior. But the center, the place where the most important features might be, where the mountain ranges and river systems and geological structures that explain everything else originate, is simply invisible. Hidden not by distance or faintness, but by the accident of where you happen to be standing. That is the situation astronomers faced when they tried to identify the Great Attractor directly. The Milky Way is a disk, a flattened structure of stars and gas and dust that we are embedded within. When we look along the plane of that disk, in the directions along the galactic equator, we are looking through the densest and dustiest parts of our own galaxy. Stars, gas clouds, molecular dust lanes, all of it absorbing and scattering the light from anything behind it. A wall of our own galaxy standing between us and the view. In the direction of the Great Attractor, roughly toward the constellation Centaurus at a distance of around 250 million light years, The zone of avoidance is particularly dense. Optical telescopes, which detect visible light, simply cannot penetrate it. The dust absorbs too much. The foreground stars are too numerous. The signal from whatever lies behind is lost in the noise of our own galaxy. So astronomers did what astronomers do when visible light fails them. They looked at other wavelengths. X-ray astronomy was the first significant breakthrough. X-rays from distant sources can penetrate cosmic dust far more effectively than visible light. Surveys of the sky in X-ray wavelengths began to reveal the presence of galaxy clusters in and around the zone of avoidance that optical surveys had missed entirely. One of these clusters, Abell 3627, also known as the Norma cluster, was found to be a massive concentration of galaxies sitting close to the direction of the Great Attractor at approximately the right distance. The Norma cluster is genuinely enormous. It contains thousands of galaxies. It is one of the most massive galaxy clusters within a few 100 million light-years of the Milky Way. For a time, it seemed like the mystery was solved. The Great Attractor was the Norma cluster, a massive concentration of galaxies sitting behind our own galaxy's disk, hidden but now revealed by X-ray observations. Except that the mass of the Norma cluster, enormous as it is, was not quite enough. The gravitational pull required to move our galaxy and its neighbors at 600 kilometers per second toward this region demanded more mass than the Norma cluster alone could provide. The numbers did not quite balance. Something was missing from the account. And then astronomers looked further. Beyond the Great Attractor, beyond the Norma cluster and the immediate overdensity that the Seven Samurai had identified, past the 250 million light-year mark toward which everything seemed to be flowing. And they found the Shapley concentration. The Shapley concentration, named for the astronomer Harlow Shapley, who first noted an unusual density of galaxies in that region of sky in 1930, sits at a distance of approximately 650 million light-years from the Milky Way. It is the largest known concentration of mass in our cosmic neighborhood. A supercluster of superclusters, a region containing dozens of galaxy clusters, thousands of individual galaxies, an almost incomprehensible concentration of matter spread across hundreds of millions of light-years. Its gravitational influence is enormous, and it pulls in the same direction as the Great Attractor. What astronomers gradually came to understand was that the motion of our galaxy, the 600 kilometers per second flow toward the constellation Centaurus, is not being caused by a single object or a single cluster. It is being caused by the cumulative gravitational influence of everything in that general direction, the Norma cluster, the various smaller clusters and filaments surrounding it, and behind all of them, at 6 times the distance of the original Great Attractor estimate, the enormous gravitational anchor of the Shapley concentration. The Great Attractor is not one thing. It is a region, a gravitational basin, a valley in the landscape of the universe's mass distribution toward which everything in our cosmic neighborhood flows. Not because of a single massive object exerting a dominant pull, but because of the cumulative architecture of matter in that corner of the observable universe. This understanding was sharpened further in 2014 when a team led by Brent Tully at the University of Hawaii published a landmark paper in the journal Nature. using a new technique for mapping the three-dimensional flow of galaxies in our cosmic neighborhood, measuring the peculiar velocities of more than 8,000 galaxies and tracing the gravitational flows they implied. Tully and his colleagues identified for the first time the full extent of our local supercluster. They called it Laniakea, from the Hawaiian, meaning immeasurable heaven. Laniakea is our home on the cosmic scale, a supercluster of galaxies spanning approximately 500 million light years and containing the mass of 100 million billion suns. It includes the Milky Way, the Local Group, the Virgo Cluster, the Great Attractor region, and thousands of other galaxies, all moving within the same gravitational basin, all flowing at varying rates toward the same central point. The Great Attractor sits at the heart of Laniakea, not as a single object, but as the gravitational center of a structure that is itself one of the largest coherent objects in the observable universe. A supercluster so vast that light takes 500 million years to cross it, that contains more galaxies than there are stars in the Milky Way, that has been organizing the matter within it through the slow accumulation of gravitational force across cosmic time. We live inside it, not at the center. The Milky Way sits in the outer regions of Laniakea, on the edge of the local sheet of galaxies, far from the gravitational focus at the heart of the structure. We are on the outskirts of something enormous, flowing slowly inward toward a center we can barely see. But here is what makes this picture genuinely strange. Even Laniakea, even this 500 million light-year supercluster that contains everything we have described so far, is not the end of the story. Because Laniakea itself is moving. The entire supercluster, the Milky Way, the Virgo cluster, the Great Attractor, all of it, is moving through space at extraordinary speed, not randomly, in a specific direction, toward the Shapley concentration, drawn by a gravitational influence that extends across distances that make Laniakea itself look like a local feature. The largest structure we know ourselves to be part of is falling toward an even larger structure beyond it. And beyond the Shapley concentration, we do not know. The zone of avoidance limits our view. The expansion of the universe limits our reach. The instruments we have built, as powerful as they are, have not yet mapped the full gravitational landscape of the cosmos to the depth required to answer the question of what, ultimately, everything in our corner of the universe is falling toward. That question remains open. And it is considerably more interesting than its absence from the popular conversation about space would suggest. Sit with the image for a moment. Every galaxy in our cosmic neighborhood, the Milky Way with its hundreds of billions of stars, the Andromeda Galaxy, our nearest large neighbor, already on a collision course with us in a few billion years. The thousands of galaxies in the Virgo cluster, the tens of thousands in the broader Laniakea supercluster. All of them, every one of them, moving at hundreds of kilometers per second toward a region of space that we can barely see directly and only partially understand. This has been happening for billions of years. It will continue happening for billions more. And most human beings who have ever lived did not know it was happening at all. The discovery of the Great Attractor and the subsequent mapping of Laniakea represents something genuinely important about the nature of the cosmos that tends to get lost in the excitement of more dramatic discoveries. Black holes, gravitational waves, the first image of a neutron star merger. These are spectacular events, singular moments detectable in hours or days, dramatic enough to generate headlines and change textbooks overnight. The Great Attractor is not a dramatic event. It is a structure, a condition, a permanent feature of the gravitational landscape of the observable universe that has been shaping the motion of matter across hundreds of millions of light years for most of cosmic history. Its influence is not a burst of energy. It is a slow, patient, inexorable pull operating across timescales that make the lifetime of a star look like a moment. Organizing the matter of our cosmic neighborhood into the web of filaments and clusters and voids that defines the large-scale architecture of everything we can see. The Great Attractor is the universe doing what the universe does, building structure, accumulating mass, drawing matter together through gravity across distances and timescales that resist every attempt to make them feel real by comparison with anything in human experience. To fully appreciate what it means that we are being pulled, that our galaxy and everything around it is flowing at 600 kilometers per second toward a gravitational basin that we can barely see. You have to hold simultaneously the scale of the thing and the intimacy of its implications. The scale is this. The observable universe is approximately 93 billion light years across. Within it, there are an estimated 2 trillion galaxies. Those galaxies are not distributed randomly. They form the cosmic web, a vast network of filaments and walls and clusters surrounding enormous empty voids. The filaments are the densest regions, the highways of matter along which galaxies cluster and flow. The voids are the emptiest regions, bubbles of near nothingness surrounded by the walls and filaments that give the cosmic web its sponge-like structure. The Great Attractor and Laniakea are features of this web, not the largest features, not the most extreme, but real features, gravitational basins within the web where matter has concentrated more than the average, drawing surrounding galaxies inward through the slow accumulation of gravitational force across cosmic time. Every supercluster has a gravitational basin like this. Every region of the cosmic web has its own internal flows, its own patterns of galaxy motion shaped by the local distribution of mass. Laniakea is simply the one we live in, the one whose gravitational flows define our place in the cosmic web. Now the intimacy. Your address in the universe, stated fully, is something like this: planet Earth, solar system, Milky Way galaxy, local group of galaxies, Virgo supercluster, Laniakea supercluster, moving at 600 kilometers per second toward the Great Attractor. Moving as part of Laniakea at additional speed toward the Shapley concentration. Moving, along with all of this, with the Hubble flow as the universe expands. You are not stationary. You have never been stationary, not for a single moment of your existence. You are on a planet orbiting a star, in a solar system orbiting the galactic center, in a galaxy being drawn through space at extraordinary speed toward a gravitational concentration hidden behind our own galactic disk, in a supercluster flowing toward an even larger concentration beyond it. Everything is moving. Everything has always been moving. And the motion is not random. It is structured, shaped by the gravitational landscape of the cosmos, pulled along paths determined by the distribution of mass across scales that dwarf every human reference point. We are small, but we are part of something enormous. something that has been in motion since long before we existed, something that will continue in motion long after any trace of our existence has dissolved, something that connects our galaxy to thousands of others in a shared gravitational destiny, a flow toward a common center that no individual galaxy chose and none can resist. The Great Attractor is pulling us. It has always been pulling us. And now, for the first time in the history of our species, we know that knowledge. The knowledge of where we are in the cosmic web, of what gravitational basin we inhabit, of what we are flowing toward, and how fast it a form of understanding that no previous generation of human beings possessed. For most of human history, the night sky was beautiful and mysterious and entirely unexplained. The stars were fixed. The universe was static. There was no sense that everything in the observable cosmos was in motion, structured, flowing along gravitational highways toward concentrations of mass that were themselves flowing toward larger concentrations beyond. Now we know. And knowing changes something. Not practically. The Great Attractor will not affect your life tomorrow or your children's lives or their children's children's lives. On human timescales, the motion of our galaxy toward the Great Attractor is imperceptible. It is a geological fact, not a daily experience. But knowing it changes the context in which every human experience occurs. Changes what it means to stand outside at night and look at the sky. Changes what it means to point at a particular region of the sky in the direction of Centaurus toward the Zone of Avoidance, and know that behind the obscuring dust of our own galaxy, hidden from direct view for most of human history, something enormous has been pulling us for longer than the Earth has existed. We did not know it was there. It was always there, drawing us forward into a future whose destination we are only beginning to understand. If this changed the way you see the motion of everything, the quiet, relentless, invisible pull of the Great Attractor on our galaxy and everything around it, the cosmic depth has more waiting for you. Subscribe, and I will see you in the next one.